Alright, in this video we're going to be going over linear search and analyzing its complexity. So I'm going to start off with a demo. So we're going to be talking about linear search in this video, and the next video is going to cover binary search. But a good way to see both of the search methods is to do this little example. So I would normally do this in the lecture room, ask a volunteer to come up and ask the volunteer to think of a number between 1 and 100. Now I'm going to perform what I'm calling linear search. Now the analogy isn't perfect, but it gets you the right idea of the efficiency of the algorithms. So let's just say that the volunteer had picked the number 75 as the number that they're thinking of. And so then I would say, okay, well, I'm going to guess your number. Is it 1? Is it 2? Is it 3? Is it 4? And they keep saying no, 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 until I get to 75, and then they say yes. So I wouldn't pick 75, that'd be terrible. But that's the idea of linear search. You just kind of like walk through a list until you get it. Now, the list isn't necessarily sorted, and some of that breaks down, but the idea is that linear search is you walk through a list one by one. Let's do the binary search algorithm now. So same volunteer, but this time I'm going to tell the volunteer, now I'm going to guess your number, but instead of just saying yes or no, I want you to tell me whether I need to go higher or lower if it's not the answer. So they're thinking of 75 again, right? So this time, for binary search, I'm going to go right to the middle, and I'm going to say, okay, is your number 50? They're going to say, nope, higher. So then I'm going to say, okay, is your number 75? And then I got it, right? And I could keep breaking down, those halves. So I could go from 50 to 75, and then if they said lower, I would go between 50 and 75 until I kind of get to the point, get to the number. And so this demo kind of demonstrates just, linear search, you have to walk all the way up to 75, where binary search, I just keep splitting until I get it, and I'll eventually get it if I continue to split and go the right direction. So binary search takes this other kind of piece of information that can be helpful. So here is the linear search algorithm. In this particular version of the algorithm, you can see that it returns a true or false Boolean, indicating that the number that you're looking for is either in or is not in the vector. That Boolean is declared outside of the loop. It is updated if it finds the value, and then it's returned at the bottom. So the question is, how many times will the comparison inside the if statement be evaluated for this vector and looking for this number? Well, with this particular algorithm, it's going to walk through all the elements in the vector, and then it's going to check every single one to see if it's the number. So even after it finds the fifth one on the second iteration, it's still going to continue to check, even though it already knows it's in there, until it reaches the end of the loop. So this is not a good way to write linear search because it's not very efficient, because you don't need to keep checking after you found it, right? So a better way to write it is to put the return statement directly in the if statement. And you can do this in a lot of places in your code, putting return statements, inside of checks, error checks, all sorts of things that really clean up your code. So instead of having an if else and then a return, or all the other variations, it's often easier to just think about it from returning directly from the if statement. So now with this new version of the algorithm, and this isn't like really a bug, I just got a little excited to put the bugs on the slide. It's more of just like a bad implementation. But the vector, same 5, but this time the comparisons inside the if statement are going to only be evaluated twice, where on this time it's going to be evaluated 1, 2, 3, 4, 5, 6, 7 times, right? Or n times. It's always going to be evaluated n times, where n is the size of the vector. So in general, linear search operates that way. So if it's written this way, the best case is that the thing that you're finding is in the first spot in the vector, right? So best case is that it's on the first index, which means that you only have to do one operation, so it's O1. The worst case then is that the thing that you're looking for is in the last index of the vector. So if that's the case, then it's going to be ON. So it's going to take however many elements are in the vector. But on average, it tends to be like, n over 2, and that's an analysis that you'll be able to do when you take the algorithms class. So on average, it's about O of n, and so we call the big O of linear search ON. And all we really care about is that linear search grows linearly in proportion to n. So what does that mean? It means that if you double the number of elements in the vector, it takes twice as more time on average to run it. And so that is the complexity of linear search. And the details of best case and worst case and average case, something that you're going to dig into a little bit more in your algorithms class, but we're going to think about it for each of the algorithms that we talk about. So best case for linear search is that you find it on the first try. Worst case is that you find it on the last try. And average case turns out to be what typically happens with linear search algorithms, and it comes out to O of n. And the big O is O of n for linear search. So here is the big O graph that I'm going to come back to for pretty much all the algorithms that we're talking about. So linear search is showing up right here on the ON line, and oh, it didn't show up on this slide. This is stuck. You can basically think of this as n and this as time. The x and y axis. Okay, so we're going to move on to binary search in the next video, but that is it for linear search.